Hello everyone, today is class number 36 for your EMFT. Class number 36. Okay, so today the last topic of this module, that is magnetic boundary condition. Okay, so write down the heading first. It will be topic number 11, magnetic boundary condition. Magnetic boundary condition. Okay, right. To determine the conditions, we use Gauss's law. To determine the conditions, we use Gauss's law of magnetostatics and Ampere's circuital law. These two basic theorems you have to apply. Okay, so Gauss's law for magnetostatics and the Ampere's circuital law. Okay, so that means closed surface integration B dot ds equals to 0. This is your Gauss's law in case of your magnetostatic system, and the Ampere's circuital law will be H dot dl, which will be equals to I enclosed. Okay, this is your Ampere's circuital law. So let us consider two system having a boundary. Okay, suppose this is medium 1 and this is medium 2. That means the system 1, or you can say it is system 1 and system 2. Okay, whatever you can say. And we are taking a cylinder at the boundary. Okay, we are taking a small cylinder at the boundary. Okay, and the parameter of this cylinder, we have to take that the height of this cylinder will be del h. Okay, it will be del h, and the surface area, whatever we have taken here, it will be del s. Okay, so now write, and the system 1 having the permeability mu1 and system 2 having the permeability mu2. Okay, so from this closed contour, if we consider from this closed cylinder, if we consider a closed contour, then it will looks like a square, because we are moving from here to here, that means here to here. Okay, so if we consider A, B, C, D, so this is your A point, a diagonal, it is B, and it will be C, and this point will be D. So A to B, B to C, C to, that is a square, that is rectangle, diagonal of this cylinder, it will be a square rectangle. So from C to D, and again D to A. Okay, we have to take this one, and the width of it we are taking del W, that means diameter of it will taking as del W. Okay, so what are the components over this rectangle? Okay, there are, suppose we are taking the intensity, resultant intensity will be looks like in this direction. Okay, so obviously at this boundary, if we consider a point and the direction of H1 will be this one, and must have the direction of H2 will be also in this direction. So this H1 having two projections. Okay, so this first projection is called your normal projection, so H1n. Okay, and this projection is called tangential projection, H1t, and this field also have two projections. Okay, this is called H2t and it is called H2n. Okay, these are the systems we have to take in here. Okay, so now apply the Gauss's law in this box, in this small box, or you can say pill box. Okay, PILLBOX. This box is called pill box, PILLBOX. Okay, so applying the Gauss's theorem, we have B1n del s minus B2n del s equals to 0. Why? Because this is your normal component. Suppose suppose we are taking here H, but we can also taking is as B. Okay, so we can take it as B also. Okay, so because we know the relation between H and B, which are very much similar, whatever you can say, if you have any problem, then you can directly assume this B over here instead of H. Okay, no problem. Okay, so b1n is nothing but in this direction. So b1n multiplied with del s and b2n multiplied with del s, that means how much fluxes are emitting from that whole surface, that will be shows by this term b1n into del s minus b2n into del s. That means this b1n del s is the amount of flux emitting from this surface, and similarly due to this first system, and similarly the b2n dls is represents the amount of flux we transmit through the surface due to the second system. And for this case we are considered this del s and this del s are identical. Okay, so that means b1n minus b2n equals to 0 as del s not equals to 0, right? So that means b1n equals to b2n. Okay, so this is your first boundary condition for air. Okay, so now thus the normal component of b vector is continuous but the normal component of h vector is discontinuous. Okay, why it is discontinuous? Because we know that is mu1 h1n equals to mu2 h2n. Okay, so we cannot write this this mu and mu are, so that means mu h1n cannot write h1n not equals to h2n. See, this multiplication of this mu, we will get the equal result. Okay, so that means this it is equal and they are not equal, okay, or unequal. So that means at the boundary surface this H, that is the magnetic field intensity, is not equal, but the magnetic flux density will be equal. Okay, so now now applying Ampere's circuital law, assuming that the boundary carries a surface current K vector. So we are taking a within this boundary a current is passing K vector. Okay, K vector, and the unit will be ampere per meter. We are taking the K vector. Okay, surface current density. So then thus K, so K into del W, which will be equals to H1T into del W minus H1N into del H by 2 minus H2N into del H by 2 minus H2T into del W plus H2N into del H by W. How? Because H1T, you can assume this H1T is what, or you can write also B1T over here. Okay, because for this case we are taking the same concept. So H1T means in this direction multiplied with del W. So we are taking in this path first. We are taking in this path. Okay. So say next C2D. So C2D over here. It is C2D. And next is H1N. H1N means this is a normal component. H1N into this is will be total del H. So total sum up will be del H by 2. Okay. So total will be del H by 2. Negative of again H2N. This is your H2N. Okay. Negative of H2N into del H by 2. And similarly it will be negative of H2T into del W. That means what? That means we are taking this direction of the flow of the K. Okay, this direction of K, flow of the K. So it will be positive, they are negative. Okay, so only the positive thing is that for this case H2N into del N by 2. Okay, by according this condition we can easily perform this result. Okay, so after calculating it, if we calculate it, then what happens? See, if we so if we take it common, H1N and H1N and H2N are very much same, right? So H2N del H by 2, H2N del H by 2, H1N del H by 2, there will be a H1N plus H1N del H by 2. Okay, they are cancelled out from both sides. Okay, so the last thing H1T del W minus H2T del W, which will be equals to K into del W. So by taking common del W and cancel out themselves, H1T minus H2T equals to K. Okay, this is your second boundary condition. Okay, this is your second boundary condition. So mu1 H1N minus mu1 sorry, b1t by mu 1 equals to b2t by mu 2 equals to k. Okay, these two are the second boundary conditions by applying your Ampere circular law. So the previous one by applying the Gauss's Gauss's law in magnetostatics, and now it is in Ampere circular law. Okay, by using the Ampere circular law. Okay, so next, so what we, and now if we consider this b1n, but here we remember b1n should be equals to b2n. This is here also another condition, b1n should be equals to b2n. Okay, b1n should be equals to b2n. It is here, you have to remember it. Okay, so then write, therefore, so what is b1n? What is b1n? b1n is nothing but this one. So if we consider this angle is theta, this angle is theta. Okay, so that means or this angle is theta 1, suppose this angle is theta 2 we are taking. Okay, so then b1 sine theta 1 by see and h1n equals to h2n, we have previously proved it. Okay, so this h1n by h1n by mu1 by mu2. Okay, so this h1n is what? If we consider it is h1n, then we can write h1 vector into sine theta 1 by mu1 equals to h2 vector into sine theta 2 by mu2 vector. Okay, so these are two basic, these are also the boundary conditions. Okay, there are few number of boundary conditions are there. Okay, and if it is same b1n equals to b2n, then you can write that b1n equals to b2n, but h1n by mu1 equals to h2n by mu2. So next line you can easily write over here. So this so b1n means b1 cos theta 1 equals to b2 cos theta 2, right? So this is another equation. So these are the boundary equations. There are several number of boundary equations can be found in case of your magnetic boundary magnetic system. Okay, so if we okay, so this magnetic boundary condition is, there are several number of magnetic boundary conditions. Okay, so next module will be your time varying field. Time varying fields. Okay, so time varying field means what? When the time is a parameter. Okay, when the time is a parameter, then you can say that the field which is assumed here, which will be time varying in nature. That means with respect of time, as the time is elapsed, some parameters and some equations are also modifying. Okay, some equations are also modifying. That means the equation till now there is no time dependency or time factors present in any equation. Okay, so the time varying field is actually produces an equation or set of equations which contains the time variable. Okay, which contains the time variable. Okay, so your time varying field for this time varying field, you have to you have to learn a number of formula. Okay, so first list down the topics. So first topic will be your Faraday law. First topic will be your Faraday's law. Okay, second topic will be induced EMF for the time varying field. Okay, induced EMF for the time varying field. Achha, remember, that means what about the Maxwell's equation we have got till now? There are 4 Maxwell's equation. All the Maxwell's equation will be modified here. Okay, will be modified here. Okay, so this induction of your EMF for the time varying field for different cases. So there are 3 cases. Okay, 1, 2, 3. 3 cases are there, and then you have to learn about the displacement current. What is displacement current? Which is very much important topic. Okay, in your exam purpose, this topic is very much important. Okay, the displacement current is very much important. Okay, so next you have to learn the short note on Maxwell's equation. Okay, so these 4 topics are very much important, and we have to learn all these 4 topics for the time varying field. Okay, and inside this topic there are 3 applications. Okay, so actually this Faraday law will produces this application. Okay, so this second point you can also call. So these are the important. Okay, before starting we can making sure that the important topics, and you have to learn very well. Okay, so this is the application for time varying Faraday law. Okay, so this is your time varying field concept, and so time varying field will start from next day. Wait for next day. I will start the time varying field. Okay, thank you.